So, I am going to start off a new module in the class. So, this has to do with algorithms for relational algebra operators, and we will also briefly look at how exactly query evaluation happens inside relational database management systems and what are the issues that are there. It is a relatively short module, so I will give you an idea, a peek into the various issues and the important algorithms. We will discuss algorithms for joins especially in this module. Okay. So, let us get going. So, if you look at the evaluation, the query evaluation, SQL query has to be translated into a relational algebraic expression, and then that expression will have to be executed in order to give results for the SQL query. So, the relational algebra expression obviously makes use of lots of relational algebra operators that we have seen already, like select, project, join, union, intersect, difference and all these things. So, we have to look at how exactly these operators have to be evaluated on their operands, right. And then the SQL query might also have grouping and aggregation, right. So, applying, so grouping involves creation of the groups, partitioning, right, and then applying some functions on those partitioned data. So, partitioning typically involves sorting, because unless you sort the tuples, you will not be able to put them into groups. So, sorting is involved. So, how to actually implement these things in the context where majority of this data is on the disk, and typically they are large size files and they are all lying on secondary storage, and so we should consider all secondary algorithms that involve secondary storage, right. So, we will focus a lot on how do we minimize the number of disk reads, how do we minimize the disk reads, and in the context of disk reads, since memory operations are so inexpensive, we will largely ignore the memory operations. Now, when we are implementing these things, obviously the indexes will help. So, the presence of index will help us a lot. So, how do these indexes help, and is there any other information that is helpful? If that is the case, how do we make use of that and how do we collect that information? All these issues are there for us to look at. Okay. Now, let us start with simple selections. Let us focus with selection condition can be on some attribute x and equal to some constant. Let's in general it can be another attribute or a little complex expression, etc. Let us just focus on the simple condition where the selection attribute equal to some constant. Now, how do we so on some relation, on some set of tuples, this kind of a selection condition has been specified. Now, one of the first things we have to check is that is there an index on that particular attribute x. If there is an index on the particular attribute x, then you know that given the value of the attribute, you will be able to quickly retrieve the records that have this specific value from the set of records using the index. The index will help us. It will give you record pointers, and so you can go, or block pointers, and then you can go pick up those files. If there is no index, then we have very little we can do. Basically, we will have to do a file scan to figure out what are all these conditions, what are all those records in which this particular condition x equals c1 holds. Of course, if so the query engine keeps kind of track of what kind of queries are being posed to this query engine, and then if this kind of a selection condition is coming often, then it might actually look at the physical organization and might actually decide saying that it's probably better off to construct an index on this particular X and then keep it ready, because I am getting too many selection conditions involving this particular attribute in case the index is not there. So, these are the various considerations that, and notice that this is a dynamic kind of a system. The system keeps learning or learning from the past as to how it has been doing. It has at least the potential to do that. Now, let us say there is a oftentimes the selection condition is not just a single condition, there may be a conjunction like this, x1 equals c1, x2 equals c2 and so on, xk equals ck. In this case actually we are relatively lucky, I can say, is that if there is, suppose there are some 5 number of these things, then if an index exists on any one of these things, any one of these attributes, if an index exists, then we can, it is a conjunction. So, we can make use of, say, let us say on x2 there is an index. So, I can go make use of the index on x2, pick up all those records whose values for x2 are equal to c2, and then in those set of records I can check the other conditions, right, because it is a conjunction. So, no file scan will be required in case there is an index on any one of these attributes. Since there are many, it is likely that you will have a index on one of them, and so we can make use of them. Of course, if you have indexes on more than one of them, then you have a choice also, then you can choose the index that has the better depth, right. In sense the average expected number of the number of discretes using that index is low. Like for example, if a hash index exists, then you can make use of the hash index. If in an unlucky situation where there is no index on any one of these attributes, then you basically do not have any choice other than doing a file scan, and while you scan the file, check this condition and then pick up all those records that satisfy this particular condition. Now, disjunction is harder than conjunction actually. If you have a disjunction, there are several disjunctive conditions. So, like x1 equals c1 or x2 equals c2 etc., or xk equals ck, then it is not sufficient if you have an index on any one of them. In fact, you have to have index on all of them, only then it will be useful. So, index on any single xi is not helpful because it is an OR condition, right. So, you basically probably will not be able to avoid a file scan in case there are disjunctive predicates in the selection condition. Now, let us also in this context we can also think about this particular quantity called predicate selectivity. Predicate selectivity. How selective is a condition? So, depending on that you can proceed, you can basically make use of this thing. So, in case there is a index on multiple attributes, then you can choose the attribute that is highly selective and then try records that satisfy that, and then go ahead and then make use of the set of records. Let me tell you what is selectivity is. Selectivity is basically the number of records that satisfy that particular condition over the divided by the total number of records that are present. So, that is what we call as the selectivity. So, here are some examples. Student department equals CSE. So, assuming that there are about 500 students or 450 students in our campus of 8,000 students, the selectivity is like this. And there are, I heard fewer number of girls compared to boys. So, the selectivity of this is like this. If you give a roll number and then look at the selectivity, that is very low selectivity. The low values for selectivity basically mean that the number of records that satisfy this is low. So, it is highly selective. So, actually the lower the number, we call it highly selective. The condition is selective, highly selective. So, your condition is said to be highly selective if the value for selectivity is low. So, if you have a conjunction of conditions, then this selectivity values will help us choose the one that has most selective condition, then that will give you the fewest number of records to handle, and then retrieve those records and then do the check for other conditions. Okay. So, get those records and then check the other conditions, that is the strategy we will use for. So, how do we get these selectivity values? So, these are some additional information that we can keep track of while the system is running. While the database is under use, you can actually keep either selectivity values or their estimates in a place called DB catalog. So, in a database catalog, we will actually along with lots of other metadata of the database, we will also maintain these statistics about the various selection conditions that are being used in queries. So, these statistics will be generally used by this query optimizer. So, as the database keeps running and then answering various ad hoc queries, on the side it will also keep track of these selectivities values. So, for example, if there are equality conditions involving a key attribute, then the selectivity will be, you can also use these rough formulas for finding out the selectivities. Even if you do not have the selectivities, you can find out the selectivities. So, selectivity involving a key attribute is 1 by total number of records in the record. So, if the equality condition involves non-key attributes, then you can make some rough estimate about the selectivity by taking the number of distinct values per attribute. In that attribute, what are the number of distinct values, and then you can assume uniform distribution of the values among all the records, and then take 1 over the number of distinct values as the estimate for the selectivity. Okay. Sometimes the database systems also even maintain a histogram. So, a histogram will have on the horizontal axis either a distinct value of the attribute or a range of values, and on the vertical axis it will have the number of records that have that particular value, or the value range exists within that range. Okay. So, on the x axis we have either the distinct values or ranges of distinct values, and then on the y axis we have the number of records that have that. So, given a particular condition, so you can go check the condition, the constant value that has been given for that particular attribute, use this histogram and figure out how many number of records are possibly there in the data file, estimated to be there in the data file. So, this also will be can be maintained offline, and then you can keep it updated as the system is running. Now, moving on to projection operation. Projection operation is somewhat costly actually because this requires you to choose a particular set of attributes from a record. That is what projection is, right. So, for every record that is there in the operand, you basically have to access this and then take the required attributes, values, and construct the result record. and of course, duplicate elimination is also involved. If you know as a result of doing this, in the result records, if there are duplicates, you will have to eliminate them. So, sorting so duplicate elimination is somewhat costly operation, and we basically either have to use sort or hash based methods for duplicate elimination. We will shortly consider the sorting operation in detail actually. So, the file scan becomes kind of essential for project operation, and the rough one of the ideas that we can make use of is to try and apply this projection after the selections. Do the selections, then you have fewer number of records, and then on them do the projections wherever possible. Essentially, this will reduce the amount of input that is given to the project operand. Okay. Now, so this is about selection projection. Before we move on to joins, one has to kind of consider this sorting, because it's really one of the important things that are required when we are looking at execution of queries, because sorting kind of appears in some step or other, because either you have to do duplicate elimination or you have to do grouping, or sometimes we can actually use sorting as a method of joining also, joining records. I will talk about sort based joins, especially if one of the file is sorted, then it might be actually advantageous to sort the other file and then merge these two files in order to do a join. We will come to the join operations a little later. First, let us focus on external sorting. So, external sorting basically involves that you have a huge file which is disk resident, and you have been given some attributes for comparing the records, and you have to sort them in the increasing order of those records. So, the merge sort principle is used. In this case, merge sort principle is used. Merge sort is familiar to you. So, basically it is a order n log n worst case complexity algorithm for sorting n items. So, we have discussed it in the data structures and algorithms course for in memory sorting, right. So, given an array, how do you sort it using merge sort principle and all that you would have studied. We will basically adapt that principle here, but then pay attention. It's not like completely straightforward to kind of do it on a disk file. So, there are some issues involved. So, we will look at them carefully. So, in the external sorting, while we are using merge sort principle, there are usually two phases that has to be considered. One is called the sort phase, the other one is called the merge phase. Well, the sort phase you might slightly get confused. I mean, if you are already sorting, what is the question of merging? You might confuse, but sort phase actually is to create many sorted sub files. Actually, you will create many sorted sub files of the main of the data file. These sorted sub files are called runs. In the database parlance, we call them a run. It's a bunch of records already sorted, but it is not the whole data file. It's a part of the file. So, basically read part of that file, sort it and write it back to the disk, then you would have created one run of the thing. So, like this you will create several runs. Once you create, so in the sort phase we create several sorted runs, and then in the merge phase take some of them, merge them, and then produce a ultimate sorted file. So, that is how the rough idea is. So, in fact, what we will do is we may not be able to merge all of them together. So, take some of them, merge them and write it back and repeat this process till you are left with the one sorted file. Okay. So, let me tell you the details. So, I will give you a little bit more in detail now how exactly the external sorting works. Okay. So, the sort phase, so the essential assumption that we are making here, is that the data file has some huge number of blocks, let us call it n blocks, and we need to, we cannot fit all of those data, all of the entire file into the memory. So, we have been given some memory space, so which is of roughly equal to, m number of blocks. M might be huge, but still n is much larger than m. So, you have some memory space, RAM space, which is equal to m blocks, okay. And the disk file is having some n blocks, which is a huge bigger number compared to m. So, in the sort phase, what we will do is, so if there are n blocks, we can read m blocks into the memory at a time. So, we will have, in order to read the all the file, all the blocks of the data file, we will take n over m number of iterations. Okay. So, repeat the following n over number of n by m seal times. So, each time what do you do? Read the next m blocks or a part of it. The last time, I mean, you may be having less than m blocks. So, read the next m blocks, sort them in memory, and then write the disk as a single file called run. Okay. So, in this process, we would have created each time. So, notice that we are actually not sorting the entire data file here, because we are not reading the entire data file into the memory, we cannot. So, whatever part of it we can read into the memory, we are reading. So, m blocks we are reading at a time, sorting it and then writing it back onto the disk. So, you are now creating sub files of the main data file, and each of these sub files is sorted. And we do not count the sorting time in memory. Okay, what is the complexity of this whole thing is, so how many number of sub files you will create now? This n by m number of sub files you would have created. There are n number of data blocks, you are reading m of them at a time. So, in order to finish reading all of them, you will make n by m number of iterations. So, each iteration you will produce one sorted subfile. So, these things are called runs, and so the number of runs is n by m seal. And the complexity of this entire phase is 2n block accesses. Why is that? Basically, you have to read all the n blocks of the file into the memory at some time or other, and then basically write them all back, right. You will have to read m blocks at a time, the whole data file, sort them and write back those m blocks again. So, essentially you are reading all the data file blocks and then writing them back. So, it is 2n block accesses, 2n block accesses. Are you all with me on this? So, at the end of sort phase, what we have done is to create some r number of sub files, each of which is sorted. Now, we can actually do merge. remember that in the in-memory case, we always assume that the whole data fits into the memory, and so we will assume that some portion is already sorted. In fact, each record is treated as a sorted thing, and then we will merge two of them together into one sorted block like that, and then merge the two records into 4 records and so on and so forth. That is the in-memory sort algorithm, merge sort algorithm, remember. But here we are looking at what is available space. The buffer space is m blocks. So, we can read that much portion of the data file, sort it in memory and then write it back. So, that is the basic unit of sorted sub files we have. Now, we take all these sorted files and merge them, just like we did in the usual merge sort algorithm. Okay. So, the starting point is this number of R runs. Okay. So, let us focus on merge now. So, if the file has n number of blocks and the memory buffers are m, which is at least 3 blocks or so, and the number of runs is r, then we can, in the in-memory case, we always merge two things and then produce one. But actually here we can do a d-way merging. I mean, the d will be at least 2, but can actually be a large number. What is that large number? It is m minus 1, where m is the number of memory buffer blocks that are available to us. Why minus 1? Because we have to keep the result somewhere. After we merge, we get the result, right. So, we have to keep the result somewhere. So, we allocate one block memory, one block for that, some amount of space for that, and the remaining remaining entire space we can afford to use for merging purpose. Okay. So, that is the essential idea. That is why we can actually do a d-way merging. What is a d-way merging? A d-way merging is look at d of these records, put them in sorted order and write them back. That is a d-way merging. So, a two-way merging is look at two of them and then compare them and then write them in the appropriate order. That is two-way merging. Well, now we will do a d-way merging, where we look at d of these things at a time and then sort them and then write them back. Okay. Write them back means I will show you how exactly we will write them back. Okay. So, now let us look at the algorithm. For example, the merge phase has this thing, repeat the following, we will see how many times it will come to. So, basic idea here is that if you have some runs, some number of runs, we will reduce this number of runs to that run divided by d, number of runs. Okay. So, that means if you have some 100 runs to start with and then you are doing a 4-way merging, so we will reduce the runs to 25 runs. You will take 100 runs and produce 25 runs. Okay. So, reduce j runs to j by d number of runs. Initially j equals the number of runs that we have. How do we do this? How do we do this j runs into j by d runs? That is our usual merging actually. So, by repeatedly merging these d runs at a time to get one run. So, how do we do? Use d buffers. Use d buffers. That is why d is at most m minus 1. Use d buffers, one for each of these d runs that we are talking about, and use one of these buffers, one of the other buffer, use the other buffer for the result. Okay. So, get one block at a time from each of these runs. Each of these runs is a huge file again. So, get one block at a time from each of these runs, merge and write the result to the disk. This you can afford to do because each of those runs are already sorted. Each of those things are already sorted. So, you can consider the topmost block in each of those runs, and then if necessary, yeah. So, I will show you a diagram also for that. Merge and write the result to the disk, one block at a time. So, what is the complexity of this? So, how many number of times do you have to repeat this? Reduce the j runs to j by d number of runs. How many times you have to do? It's log r to the base d. Here you have r runs to start off. Each time you do a d way merge, you reduce this r runs to r by d runs, and the next phase you will reduce it by r by d square and so on. So, a factor of d is the reduction in the number of runs, and so the number of times this whole thing has to be done is essentially log r to the base d c. That many number of times you have to do. So, if you have 1024, okay. So, you know what is the log function, so I do not have to repeat that. And now, so since you are doing this log r to the base d number of times the whole thing, and what is this thing doing? In each of these phases we are reading all the runs. We are reading all the runs and then converting them into a fewer number of runs. In essentially we are reading the whole data file. In each of these subphases, we are actually reading the whole data file, because the whole data file records are actually spread over this r number of runs. We are reading all those runs and then reducing them to r by d number of runs. But the run, if you take the lengths of the runs, in both cases, if you total up the length of all those runs, it is the same, because you have read all the records and then written them all back. You get that point? The number of runs are reducing, but the number of records is not reducing. The number of records are all spread over all these runs in appropriate places. Each of those runs is a sorted run. So, you are taking two of them and merging them and then producing one. So, the number of records will not disappear, right? It will all be there, right? If you are taking 100 of them and then producing 25 of them, the same number of records will be there in these 25 runs. So, each time you are reading the whole data file and writing it back. So, you are doing 2n block accesses. If n is the number of blocks that are there in the data file, you are actually doing 2n block accesses. And how many times are you doing this? As many times as there are requirements, like log r to the base d. This many number of times you are reading the data file. So, the complexity in terms of block accesses, that is what we care about in this course, right, block accesses. This merging actually takes some memory time, but we do not care a bit about it. So, 2n log r to the base d is the number of block accesses that we will require, and then this is only the merge phase. What about the overall? In the sort phase, we had used 2n block accesses. So, in the sort phase, we have used as 2n block accesses in order to create the initial set of runs. And in the merge phase, we are using 2n times log r to the base d number of block accesses. So, this is the overall number of block accesses you have to do in order to sort a file, an external sorting, using the most efficient algorithm, merge sort. You know that merge sort is one of the best sorting algorithms, right? Worst case n log n, very happy situation. Okay, so let me show you a diagram here which will make this whole process a little bit easier to visualize. So, let me take the crucial step of reducing this j runs to j by d number of runs. So, at this time you have 1, 2, 3 up to j runs. So, all your records are spread somewhere here in those j runs. You are taking d of them and then merging them and then creating one run, a new run. Okay. So, now because you are taking d of them together, so this j runs will now become j by d number of runs in the next phase, and then you have to repeat that. Again, take d of these runs and then merge them, then it will become j by d by d, j by d square number of runs here. Okay. Now, let us focus a little bit on how do we exactly merge. So, take each of these j runs, some number of runs. So, some number of runs. For each of them, this is a d way. So, there are d number of buffers that we can make use of, and there is one buffer that is for keeping the result. So, d number of memory buffers. These are green things are memory buffers. And so, here you can maintain pointers, the memory pointers. Okay. So, you have seen in merge sort implementation, the pointer has to be moved accordingly, right. So, now you move the pointer inside the block actually. So, now you have fetched one block here. So, each of these blocks has data which is tuples, records. So, now you look at the topmost of all these things, they are already in sorted order, they are all in sorted order. So, now look at all of those things. Obviously, one of these things will be the first among them, sorted. So, pick up that, advance the pointer there. Wherever you pick up a record, you advance the pointer there. And then again look at all the pointers, pick up the next one, advance the pointer there. So, in the process of advancing the pointers, advancing means you are coming down, you might exhaust the block. If you are exhausting block, fetch a block from the sorted file into the buffer. So, that way slowly you are getting all the blocks of the sorted file into the thing. So, in case one of the runs is smaller compared to the other one, this might become empty. So, ignore that pointer, merge the other records. So, basically keep merging like that, and as you are picking up the topmost records from this entire set of records, keep putting them onto the result, and the result will start filling up, result block will start filling up. Once a block fills up, write it to the disk, keep shifting the records to the disk. So, you have taken j runs and then you produced a j by, you have taken some d runs and produced one run. Okay, is the process clear? So, sorting, even though we know the principle that we are using, which is merge sort, is a little involved in external methods. So, this is how you can actually do a sorting, and the overall complexity, as I told you, is, so it is a pretty costly operation. So many number of block accesses are involved. Okay. So, let us move on to join is a very important operation obviously. So, let us focus a little bit on two-way joins. So, two files of records and a join condition is given, you are supposed to join. In a multi-way join, you are given more than two files and a join condition, you will have to join. Now, what is the choice of algorithm for doing a join? Kind of depends on the sizes of the files that are involved and what is the primary organization of those files. How are those files organized? Are they already sorted files? If they are already sorted files, I can do while doing merging, I can do join actually. something similar to merging I can keep doing, and in that process I can actually pick up joined records. We will just consider equi-join, let us say, we will consider equi-join if, okay. And are there indices available? So these are some of the questions. And what about the selectivity of the join condition? What is the selectivity of the join condition? So these are the various things that are involved. Let us consider one brute force kind of a join. Let us say we do not have any indexes on those files. So what is the brute force way of joining? This algorithm is called nested loop join or block nested loop join. So essentially the join algorithm is very simple to state. For each record x in R and for each record y in S, so this is a inside loop. So as you are iterating each record x in R, you are looking at all records in y, and if checking x and y are joining, means they together satisfy the join condition, if so produce the join output. So this is the simplest of approaches. But then again considerations will come into picture, because you have R has some B1 number of blocks, R2 has B2 blocks, and we always have some M number of buffer blocks. Some amount of memory is available, and we will measure it in terms of blocks because it is easier for us to handle the numbers that way. So M, let us say we have M buffer blocks. So if we have buffer blocks, then basically we will keep one block for the result of the join and keep one block for the inner file. Let us say S is the inner file here, right. So inner file, we will call it inner file, and the remaining M minus 2 for the outer file, M minus 2 blocks for the M minus 2 buffers for the outer file, and the algorithm is very simple. For each set of these M minus 2 blocks of R, so we will obviously not be just reading records of R into the memory, because we have to do block accesses. R is a disk file. So we will pick up M minus 2 blocks of R at a time. Maybe we will be able to, we get fast access if you give a large number of consecutive blocks of a file, we do get quick access if you are using RAID and other architectures. So you will specify M minus 2 blocks and read them. So keep M minus 2 blocks of R in memory. Now keep reading the other file one block at a time. For each record in S, right. So we have to read the entire S, each one block at a time, and once we read one block at a time, we can actually do a computation, figure out which of those records of S will join with any of those records of R. So read it, compute the join, write the result, block. So write the result to the in-memory block for temporarily, and as soon as the block fills in, you can keep actually writing it back to the disk. So that is how the nested loop or block nested loop join will work. Now let me close with a small calculation here. Let us look at the time taken for doing a nested loop join. So let us say you have two data files, R with B1 blocks and S with B2 blocks and M number of buffer blocks, memory blocks. So R was the outer block, right, outer file, R was the outer file. So outer file has B1 block accesses basically, because you have to read the entire outer block, but the only thing is we will read them in chunks of M minus 2 blocks at a time. So but whenever we read M minus 2 blocks of the outer file at then we will read the entire inner block, inner file, sorry. The inner file is S, we will read the whole blocks of the inner file. So, how many number of times the inner file blocks are accessed? It is B1 divided by m minus 2, B1 divided by m minus 2, this many number of times we will be accessing the inner file, S file. So, overall if you look at the nested loop join, it will take B1 block accesses to read the outer file, and B1 divided by m minus 2 seal times B2, B2 is the inner file, this many block accesses. So, this file has to be repeatedly read for a chunk of the outer file. For a chunk of the outer file you have to read the entire inner file, and then you get the next chunk of the outer file, read the entire inner file again. That is the block nested loop algorithm. So, overall is this B1 plus this many number of times, and there is nothing great about R to keep it in the outer block and S to keep it in the inner block. We can actually switch them into things, and so symmetrically speaking you will get the B2 plus B2 by m minus 2 times B1, and you can see that the second term is roughly equal, it is basically B1 times B2 divided by m minus 2 in both these expressions, and it is this B1 or B2 that actually dictates the time, also differentiate these times. So, which file to keep in the outer loop? Basically the one that has smaller number of blocks. The one that has smaller number of blocks, if we can keep it in the outer loop, then that will be a additive value here, and so you can get a better access to it. So, I have some numbers here to illustrate that, but I think I will leave it to you to figure it out. So, there is some. So, we will stop here for today. Let me probably show, I will just start off with this example in a minute.